Hello friends, my name is Tushar and today I'm going to talk about Introduction to System Design. Pretty much on a daily basis, I get tons of emails and messages asking how do I prepare for system design? What are the topics to prepare for system design? Hence, I decided to create this video. System design is a very subjective topic, so whatever I'm going to say here is just based off my experience and talking to friends and peers. In this video, I'm going to talk about the basic things you need to do in the interview, but most of my time is going to be spent on talking about the topics which are very important for system design. So next, let's start with the ABCDs of system design. A stands for Ask Good Questions. It's your responsibility to ask good questions and define the minimum viable product for the system design problem. A problem could have many features and it's your responsibility to work with the interviewer and figure out which features he cares about and which features he does not care about. Remember, you're working under a very strict time frame, so make sure that your feature set is small and you go deep into this feature set. The second thing to ask about is how much the system should scale. So for example, how much data you need to store in the database, or how many requests per second needs to be handled, or what kind of latency is expected from the system. B stands for Don't Use Buzzwords. Suppose tomorrow is your interview and you read about this consistent hashing for 10 minutes today. Don't just go to the interview and start throwing those words in the interview. It might work sometimes, but it does not work most of the times. In fact, it backfires. So make sure whatever technologies or concepts you're mentioning in the interview, you have some sort of in-depth knowledge on those technologies. C stands for Clear and Organized Thinking. So before jumping into the minor details of the problem, first try to define the 50,000 feet view of the problem. Make sure you have defined all the APIs. Make sure you draw the right boxes. Make sure you understand who are the actors for the system. Once you have defined all those things, then go deeper into the details working with the interviewer. And D stands for Drive Discussions. I have a very simple 80-20 rule. You should be talking 80% of the time and interviewer should be talking 20% of the time. So make sure you lead the discussion. Make sure you anticipate the problems which are there in your solution and fix them preemptively. So obviously ABCDs are much easier said than done. You can improve on them by three aspects. First is your personal experience. If you're working on high-scale system, it's much easier to improve on those things or solve those things on a whiteboard. Second is through practice. So think about a system design question and work with your friends and peers and brainstorm those ideas and see what technologies you can use to solve this problem. And third is gaining knowledge through reading blogs and going through videos and things like that. So next, let's talk about some of the basic features which is required in a system design problem solving. First thing you need to work with the interviewer is on the features. This goes back to defining the minimum viable product by asking good questions to the interviewer. For example, if interviewer asks you to design a Facebook Messenger, then some features you would want to include is one-to-one chat, and if to show the fact that the other party received the message and read the message and so on. And some features could be excluded like group chat or security around these things. So feature is something you have to work with the interviewer to figure out what he or she cares about and what they don't care about and can be excluded. The second thing is defining APIs. Now that you're set on the features, you need to figure out what are the APIs for your service which are going to implement those features. So what are the APIs, who is going to call those APIs, how are they going to call those APIs, or things like that which you need to figure out during the second step. Third is availability. So now that you have come up with a service, you need to figure out how available this service is. For example, if a host went down, is the service still going to be available? Or heck, if the entire data center went down, would the service still be available? And you have to discuss with the interviewer to figure out how much availability he cares about in the system. Fourth is latency performance. So if it's a background job, then you do not care too much about the latency. On the other hand, if it's a customer facing request, then obviously you want your system to be super fast And based on the requirements, you might want to add a cache and things like that to improve your latency. So that's one of the aspects you need to care about while designing your system. Then we have scalability. Now you design a service, it works for 100 users, but the question is it going to work for 1,000 users, or is it going to work for 1,000,000 users, and things like that. So that's scalability. Is it going to scale as we add more users or more requests? Is it continue to have the good latency performance? Is it continue to be available as we add more and more users? So that's again you need to consider in your design solution. Then we have durability. Durability might be important for some interviews, might not be important for some other interviews. So durability is the fact that data can be stored in a database securely, and data is not lost, and data is not compromised. So sometimes it's okay to say that, hey, I will use this database and that database will do all the job for me. On the other hand, in other interviews where you are designing the database, that's the place where durability plays a central role, and you need to make sure that your system is durable enough. Then we have class diagrams. So sometimes you get questions like design a parking lot or design an elevator system, and in those questions, sometimes the interviewer is interested in knowing how you would design the class and what are some of the object-oriented principles you would use for solving those problems. Then we have security and privacy. Again, in most of the interviews, you will probably not care about security and privacy, but let's suppose the question you get is design an authentication system. And if you're given such a question, then in that question, security and privacy will play a central role. And finally, we have cost-effective. So whatever solution you suggested, is it a cost-effective solution? Is there an alternate solution which would be more cost-effective? So you have to discuss some pros and cons of different solutions as far as cost is concerned. So now that we know some of the basic things we need to do in the interview, next let's jump onto the concepts and topics which we care about, which you should know before going into a design interview. These are some of the concepts which you need to know to improve your system design problem solving. Although it's a big list, by no means it's an exhaustive list. So what I'm going to do today is go through them one by one and give a one-liner explanation on each of the concepts. Obviously, I cannot go into too much detail because frankly speaking, each of them deserves a video of their own. So let's start with vertical versus horizontal scaling. So if you need to scale up your system, either you can do vertical scaling, which means that you add more memory, CPU, and hard drive to an existing host, or you do a horizontal scaling, which is to keep one host small, but instead add another host. So vertical scaling can be expensive, and also there is a limitation of how much memory and CPU you can add to a single host, but it does not have distributed systems problem. On the other hand, horizontal scaling, you can infinitely keep adding more hosts, but you have to deal with all the distributed system challenges. So obviously horizontal scaling is more preferred than vertical scaling. Second is CAP theorem. CAP stands for consistency, availability, partition tolerance. Consistency is saying is that your read has the most recent write. Availability says that you will get a response back. It might be the most recent write or might not be the most recent write. While partition tolerance is saying is that between two nodes you could be dropping network packets. So what CAP theorem says is that you can only achieve 2 out of these 3 things. And partition tolerance, you have to have partition tolerance because you drop network packets. So basically you're choosing between consistency or availability. The traditional relational databases, they choose consistency over availability, which means that they could be less available, but their data is always consistent. On the other hand, NoSQL databases, they prefer availability over consistency if you choose to configure it that way. Next up is ACID versus BASE. ACID stands for atomicity, consistency, isolation, and durability, while BASE stands for basically available, soft state, eventual consistency. ACID is used more in terms of relational databases, traditional relational database, while BASE is used more for NoSQL database. And you need to understand the differences because once you start using more NoSQL databases, you need to understand which part of ACID properties you are willing to sacrifice. Then we have partitioning or sharding of data. Let's suppose you have trillions of records, and there is no way you can store the trillions of records in one node of a database. So you need to store them in many different nodes of a database, and that's where sharding comes into the picture. How do you shard or split this data such that every node of a database is responsible for some of the records of those trillions of records? And one technique used heavily is consistent hashing, and you definitely need to know how consistent hashing works. What are some of the advantages which consistent hashing brings to the table? Then we have optimistic versus pessimistic locking. So let's suppose you're doing a database transaction, and in the optimistic locking, you do not acquire any locks, but when you are ready to commit your transaction, at that point you check to see if no other transaction updated the record which you are working on. On the other hand, on pessimistic locking, you acquire all the locks beforehand, and then you commit your transaction. Both of them have their advantages and disadvantages, and you need to understand when to use which of this locking to use in what scenario. Strong versus eventual consistency. So here, strong consistency means that your reads will always see the latest write, while eventual consistency means that your reads will see some write, and eventually it will see the latest write. So strong consistency is obviously used in relational databases. In NoSQL database, you have to decide if you want strong versus eventual consistency, and the benefit with the eventual consistency is that it provides higher availability, and this all goes back to the CAP theorem. Next up is relational database versus NoSQL database. These days I see that most of the people prefer to use NoSQL database, and that's fine, but do not discard relational database just yet. Remember, relational database provides all these nice ACID properties, while NoSQL database scales a little bit better and has higher availability. So depending on the situation, depending on the problem, try to see which one of the two fits better. Types of NoSQL database. The first one is key value. So these are the simplest kind, where you have a key and you have a value, and it stores this key value pair into the database. The second one is wide column database. So in wide column database, a row can have many different formats, many different kinds of columns, and it can also have many columns. That's why it's called wide column database. Then we have document-based database. In this kind, if you have a semi-structured data, or if you have an XML or JSON data, and if you want to persist that into the database, then you would use document-based NoSQL database. And the final one is graph-based. Let's suppose you have entities, and let's suppose you have edges or relationship between these entities. So basically, if you have a graph, then graph-based NoSQL database is used to hold that graph. Caching is used to speed up your request. If you know that some data is going to be accessed more frequently, then store it in the cache so that it can be accessed quickly. Caching are of two types. One is if every node does its own caching, so the cache data is not shared between nodes, and the second one is called distributed cache, where the cache data is shared between different nodes. If you're doing caching, you have to consider few things. First, cache cannot be the source of truth. Second, cache data has to be pretty small, because cache tends to keep all the data in memory. And third, you have to consider some of the eviction policies around cache. Then we have data centers, racks, and hosts. So this is just saying is that you should be aware how the data center is architected, or how data centers are arranged today. So data centers have racks, and racks have hosts. So you have to understand that what is the latency between talking cross racks or cross hosts or even cross DCs, or what are the worst case can happen if an entire rack goes down, or heck, if the entire data center goes down. Then we have CPU, memory, hard drive, and network bandwidth. All of these are limited resources. So when you're designing your system, you need to consider how do you work around these limitations, and how do you improve the throughput, latencies, and scale your system around these limited resources. Then we have random versus sequential read and write on the disk. We know that reading and write on the disk is usually slow, but sequential reads and writes are actually amazing for the disk, so you should design your system around sequential reads and writes, while try to avoid random reads and writes, which are order of magnitude slower than sequential reads and writes for the disk. Next up is HTTP versus HTTP2 versus WebSocket. So HTTP is a request-reply kind of architecture between client and server. Pretty much the entire web runs on HTTP. HTTP2 does some of the improvements on the deficiencies of HTTP, like it can do multiple requests over a single connection. And then we have WebSocket, which is fully bidirectional communication between client and server. So it would be good to know some of the differences between them and some of their inner workings. Next up is TCP/IP model, and there are 4 layers in TCP/IP model, and it's good to know what each layer does. Then we have IPv4 versus IPv6. So if you know, IPv4 has 32-bit addresses and IPv6 has 128-bit addresses. We are running out of IPv4 addresses, so the world is migrating towards IPv6, and it's good to know some of the details around that, and also how does the IP routing works. Then we have TCP versus UDP. TCP is connection-oriented, reliable connection, while UDP is unreliable connection. So if you're if you're doing a streaming of video, then you are better off using UDP, because it's although it's unreliable, it's super fast. On the other hand, if you're sending some documents, then you're better off using TCP. Then we have DNS lookup, domain name server lookup. So if you type www.facebook.com in your browser, then DNS, the request goes to the DNS, which does a translation of this address into an IP address. So it's good to know how those things work, what is the hierarchy around them, how do they do caching, and things like that. Next is HTTPS and TLS. TLS is transport layer security. So it is used to secure communication between client and server, both in terms of privacy and data integrity. And when used with HTTP, it pretty much becomes HTTPS. Next is public key infrastructure. This is used to manage your public key and your digital certificates. And certificate authority is a trusted entity which tells you if the public key is from the correct party. For example, if you type www.facebook.com in your browser, and if this is going over HTTPS, then you will get a public key back, and certificate authority is used to tells you that this public key is definitely coming from Facebook and not coming from a third party who has hacked between you and Facebook. Then we have symmetric and asymmetric encryption. Asymmetric encryption is computationally more expensive, so it should be used to send small amount of data, preferably a symmetric key. So example of asymmetric encryption is public-private key encryption, while example of symmetric encryption is AES. Load balancers sit in the front of a service and delegate the client request to one of the nodes behind the service. This delegation could be based on round-robin basis or the load average on the nodes behind the service. Load balancers can operate at L4 or L7, and these are the levels for OSI model. So at L4, load balancer considers both client and destination IP addresses and port numbers to do the routing, while at L7, which is an HTTP level, it uses HTTP URI to do the routing. Most of the load balancers operate at level 7. Then we have CDNs and Edge. CDN is Content Delivery Network. Let's suppose you are watching Netflix from Seattle. So what Netflix will do is it'll put the movies and series in a content delivery network close to you in Seattle. So when you're streaming the movie can be streamed right there from the CDN close to you instead of all the way from the data center, and this helps both in performance and latency for the end user. And then Edge is also a very similar concept where you do processing close to the end user. Another advantage Edge provides is that it has a dedicated network from the edge to all the way to the data center, so your request could be routed through this dedicated network instead of going over the general internet. Blue filters and count min sketch are space efficient probabilistic based data structure. Blue filter is used to decide if an element is a member of set or not. Blue filter can have false positives, but it will never have false negative. So if your design can tolerate false positive, you should consider using blue filter because it's very space efficient. Count main sketch is a similar data structure, but it is used to count the frequency of events. Let's suppose you have millions of events and you want to keep the track of top K events, then you can consider using count main sketch instead of keeping the count of all the events. So for a fraction of space, it will give you an answer which will be close enough to the actual answer with some error rate. Then we have Paxos, which is used to derive consensus over distributed host. Before Paxos came along, finding consensus was a very hard problem. An example of consensus is doing a leader election among a distributed host. I do not expect you to know how Paxos work internally, but it's good to know what are some of the use cases which Paxos solves. For design patterns, things like factory methods and singletons are good to know, while for object-oriented design, things like abstractions and inheritance are some of the things you should be knowing. Virtual machines are a way of giving you an operating system on top of a shared resource such that you feel like you are the exclusive owner of this hardware, while in reality that hardware is shared between different isolated operating systems. While containers is a way of running your applications and its dependencies in an isolated environment. Containers have become extremely important and they run a lot in the production environment these days. Then we have publisher subscriber over a queue. So publisher publishes a message to a queue, a subscriber receives that message from the queue. And this pattern has become extremely important in the system design these days, and you should definitely use them whenever you have an opportunity. One thing to remember is that customer-facing requests should not be directly exposed to a pub/sub system. Then we have MapReduce, which is used to do distributed and parallel processing of big data. Map is filtering and sorting the data, and reduce is summarizing that data. And this is something which is very important if you're working in a big data field. And finally, we have multi-threading, concurrency, locks, synchronization, and compare and set semantics. And these are all very important to know in the world of multi-threading. Some programming languages like Java comes with these things built in, while other languages like C, you have to depend on the platform-specific implementations. So this is all I have to talk about some of the concepts. Next, let's look at some of the actual implementations of these concepts. These are some of the tools which are useful not just for the system design interview, but also in real life if you're going to work on a high-scale system. Obviously, this is a very small list and there are many other tools out there, but in the interest of time, I've kept it restricted to this small number of tools. So the first one is Cassandra. Cassandra is a wide column, highly scalable database, and it's used for different use cases like simple key value storage, or for storing time series data, or just your more traditional rows with many columns. Cassandra can provide both eventual and strong consistency. Under the hood, Cassandra uses consistent hashing to shard your data, and also use gossiping to keep all the nodes informed about the cluster. The second is MongoDB or Couchbase. So if you have a JSON-like structure and if you want to persist that, then MongoDB works perfectly fine. They provide ACID properties at a document level, and they also scale pretty well. If you have a more traditional use case with many tables and relationships within these tables, and if you want full set of ACID properties, then I would go ahead and use MySQL database. And MySQL database also has master-slave architecture, so it also scales up pretty well. Memcached and Redis are distributed cache, and they hold the data in memory. Memcached is simple, fast key value storage. Redis can also do key value storage, but it also does a lot of other things. And Redis can also be set up as a cluster, so it can provide things like more availability and data replication. Redis can also flush data on the hard drive if you configure it to do so. Two things to remember when using distributed cache. First is that they should never be the source of truth, and they can only hold limited amount of data, which is limited by the amount of memory on the host. Zookeeper is a centralized configuration management tool. It is also used for things like leader election and distributed locking. Zookeeper scales very well for the reads, but does not scale that well for the writes. Also, since Zookeeper keeps all data in memory, so you cannot store way too much data in the Zookeeper. So if you want to store small amount of data, which should be highly available and which has tons of read, then Zookeeper is what you should be using. Kafka is a fault-tolerant, highly available queue used in publisher-subscriber or streaming application. Depending on your use case, it can deliver message exactly once, and also it keeps all the message ordered inside a partition of a topic. Nginx and HAProxies are load balancers and are very efficient. For an example, Nginx can manage thousands or even tens of thousands of connections from a client from a single instance. Next up is Solr and Elasticsearch. Both of them are search platform on top of Lucene. Both of them are highly available, very scalable, and fault-tolerant search platform, and they do provide things like full text search. Next is Blobstore. Let's suppose you have a big picture or a big file and you want to store it somewhere on the cloud. Then Blobstore can be used, and a very popular Blobstore is Amazon S3, which is provided as a part of AWS platform. Docker is a software platform providing containers inside which you can develop and run your distributed applications. These containers can run on your laptop, on the data center, or even on the cloud. Kubernetes and Mesos are the software tools used to manage and coordinate these containers. Hadoop has many things going inside it. One of the things is MapReduce, and we already talked what MapReduce is, which is a processing in parallel of large data. And if you want a faster version of that, then you use Spark, which does all the MapReduce in memory. HDFS is a Java-based file system which is distributed and fault-tolerant, and Hadoop relies on HDFS for doing all its processing. This is it. This is my introduction to system design. We went through ABCDs of system design, then we talked about some of the basic things you need to do in the interview, and then we went through tons of concepts and tools. I know I went through the concepts really fast, but my intention today was not to give you too much details, but instead introduce them so that you can read them in your own time. So I'm going to put all these details and a lot of other references in the description section of this video. Please like this video, share this video, comment on this video, and check out my Facebook page. Thanks again for watching this video.